Chapter R is the first chapter of our text, and it is just a review of the real number system. So in Section R.1, we're going to introduce some basic concepts of the real number system. So the real number system is broken into number families. So the first numbers that we encounter in our youth are normally our natural or our counting numbers. So those are numbers like 1, 2, 3, 4, 5. After that, we have our whole numbers. That includes all of our natural numbers and 0. After our whole numbers, we have our integers. So that includes 0, so our whole number, our natural numbers, and then all of their additive inverses, which is something we're going to talk about later in the chapter, but that includes all the negative numbers, the negatives of the natural numbers. Next, it includes the rational numbers. Rational numbers are any number that can be written as a ratio or as a fraction. This includes all the integers, which means it also includes the whole numbers and the natural numbers. Because any integer can be written as a fraction over 1. Negative 3 over 1 is negative 3. After the rational numbers, we have the irrational numbers, and that's any number that cannot be written as a fraction. So that doesn't include any of the rational numbers or the integers. Some famous examples are pi or the golden ratio. And then the real numbers, the real number system that we're going to be working in for the majority of this course, includes all of the numbers listed above. So it includes irrational numbers, rational numbers, integers, whole numbers, and natural numbers. After the real numbers, there are complex numbers. So those numbers include the real numbers and imaginary numbers. Imaginary numbers are when you have to take the square root of a negative, which is something we'll get into further on in this course. But I wanted you to know that complex numbers exist, and we'll be working with them more closely in chapters 6 and chapters 7 and 8, yeah. And it's important to note that we call complex numbers imaginary, right? And that was first used by René Descartes in 1637. Fun little history fact. So here's the inclusion of the whole of the number system. So we've got our rational numbers, that's like pi. We've got our rational numbers like 1/2 and 3/4. Our integers like -2. Our whole numbers like 0. Our counting numbers like 1, 2, 3. And all of those together make up the real number system. When we're talking about real numbers, we can think of them as a line, right? With 0 being our origin. And we can plot all of our real numbers on a real number line. We can plot irrational numbers like pi, rational numbers like -1/2, natural numbers like 1, and whole numbers like 0, right? So we can plot all of our numbers on a number line. And the number line goes from largest, so we've got like positive infinity over here, to smallest on the left. We've got negative infinity on the left. So a set is a collection of objects whose contents can be clearly determined, and we call these objects the elements of the set. So for example, we could write the set of counting numbers or natural numbers as 1, 2, 3, 4, 5, because they start with 1, and then that ... tells us that they go on and on forever. The braces, these symbols right here, indicate that we're representing a set. So the set of natural numbers n could be denoted n is equivalent to 1, 2, 3, ... meaning it goes on and on and on until it gets to infinity. Elements are often written using set builder notation, and that uses a variable to describe the elements of the set. So for example, if x is a natural number between 5 and 11, well, that would be the set, not including 5 and 11, because it has to be between 5 and 11. That would be the set 6, 7, 8, 9, 10. That's another way to write this set in set builder notation. We could also have x, where x is a fraction between 1 and 2. Well, this is an infinite set. What does that mean? This set has infinitely many elements because I could have 1/2, 1/3, dot, 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 1/100th, dot, 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 dot. And then it goes on and on from there. I could have 2/3. So this is an example of an infinite set, meaning we couldn't write every single element in it. And that's when set builder notation really comes in handy. So here are our number families that we introduced earlier, written as sets with their symbols. So N normally stands for the natural numbers, W stands for the whole numbers. The integers are represented with the Z, and I think that's because it has something to do with the original German word for integers. Rational numbers, so numbers that can be expressed as a fraction, typically are denoted with a Q, and their set builder notation, again, because it's impossible to write every single fraction, is denoted P and Q, where P and Q are integers and Q is never equal to 0. That's because we can't divide by 0, something I'm going to emphasize as we move forward in this course. The irrational numbers are, again, any number that cannot be written as a fraction, denoted with P. We say X where, that means such that. This bar is such that. If I didn't clarify that earlier, I apologize. Such that X is real but not rational. So as long as it's a real number and it's not rational, that makes it irrational. And the real numbers, denoted with this double barred R, is any X such that X corresponds to any point of the number line. So why don't we go ahead and write the containment of the families above. So I've got the natural numbers. Those are contained in the whole numbers, which are contained in the integers, which are contained in the rational numbers. This means like containment, this like long C. And those are all contained in the real numbers. And, oh, did I skip the integers? Oh, that was supposed to be a Z. Double bar Z. Then we have the irrational numbers, and those are contained in the real numbers, but they aren't in any of our other number families. So that would be containment. Where do things reside? And again, this is just another way to draw out that picture of the containment I had shown in an earlier slide.